Okay, I guess we're about ready to get started. I'm getting a little bit of a late start because Andre was very enthusiastic about what he was doing, and so was I, and I'm probably part of the reason why he ran over. Anyway, my name's John Lakos, and we're going to be talking about today sort of basic material on value semantics, and then in the next session, which I strongly encourage people who believe that they know everything that I'm going to talk about in this session, come back and tell your friends because that stuff is really cool. Now, about the same time as Alexander Stepanov was writing this book, I gave a talk at the ACCU. Does everybody familiar with Elements of Programming? This is an interesting book. About 2011, I started reading it, and I got all the way to halfway through page 2 and got stuck. And the crazy thing is I carried it in my bag for 3 years saying, I'm going to get through this, it's not that bad, you know, and then finally Pearson asked me to do an interview on Alex's second book. So this is for Alex Stepanov. Here's the plug, From Mathematics to Generic Programming. And in order to read this book, because I'm a kind of a bottom-up guy, I had to go back and read the other book, which is part of the reason I accepted the challenge. So I went back and read the other book, and strangely enough, the first chapter of this other book says almost exactly the same thing that I came about from a very, very different perspective, which is quite heartening. So even though we arrived at the ideas from very different places, they are the same ideas to within epsilon. So there's some goodness here. I take it a step further, and I'll try to let you know where I take it a step further, and not to say that I do more, it's just that it's a little bit of a different perspective. It comes more from a software engineering perspective than it does from pure mathematics. So with that said, I'm going to get started. Here's the required copyright notice. Here's the abstract. But since you guys are already here, I probably don't need to sell you on this, so we'll skip over that. This is an outline of the talk. Now, because I'm short on time, because we know why, the introduction and background is really just a branding. So let's go to that. What's the problem? Well, you know I'm about large-scale software design, have been for a very long time, and want to just point out that this is the notion, it involves the notion of logical and physical design. Classes are logical, and functions are logical, and files are physical, and libraries are physical, and this is what a component looks like. Component is the fundamental unit of logical and physical design. It consists of an implementation file, a header file, and a test driver. What does this have to do with what we're talking about today? Nothing. But it's here, because it's branding. So we won't be talking about that. The next thing we won't be talking about is the relationships between the logical functionality embedded in a component and the physical dependencies that result from implementing it there. So you can see that I have a physical hierarchy of physical components that contain logical content. The next thing that we're not going to be talking about is how we describe the logical behavior within components in English contracts. And again, being mindful of the physical dependencies that result. So here's an example of a component class diagram with a bunch of logical relationships that in turn imply physical dependencies. This is really good stuff, but we're not going to talk about it. We really do need to pay attention to the different class categories because there are a few that we use all the time, and in particular, this talk today is about value types. So how many people feel that they have a good grasp on what a value type is? Be honest, because I want to pick on you. Excellent. Okay, that's good. Remember, this session is just about getting a feel for what we're talking about. And then the next session, we're going to really apply it on some fairly interesting problems. So this is a taxonomy. And if you go to our GitHub repository, this kind of thing exists, and it shows how you navigate across class categories. And these little bubbles that I'm putting up here are the main ones. And you'll see that there's something called a utility, a protocol, a mechanism, and a value semantic type. So those are the primary things. But we'll get to that. This is the emphasis, but we're going to get to these as we go through the talk. All right, so that was the introduction. Next. So we're going to answer some key questions about value. Hopefully somebody's going to get me some water because my throat is very dry, and I'm going to, oh, there it is. Okay, thank you. That's non-causal. All right, very good. Okay. So I put this up here because we're going to go through these one by one, but just to give you a little bit of an overview of what we're going to talk about. So getting started. Interestingly enough, the previous talk was about allocators. Well, I'll get to that in a moment. So not all classes are value types, but still value types are a very important category. Allocators, of course, we'll see are not value types. Let's begin with an understanding of some basic properties of value types, and then we'll contrast them with non-value types to create a type category hierarchy. So that, and then finally, we'll dig further into the details, mostly in the next section. This is more of a value types 101 talk. So now, to my story. So the date is October 5th, 2007, and it's my second attendance of the Standards Committee, I think, or was it the second or possibly the third? I think there was one way back in 2004 where we went to talk about allocators, and it was a lukewarm greeting, let's put it that way. But by this time, we had gotten to the point where we were proposing a different kind of allocator, and unfortunately, it made it all the way to the full committee, and then because of this thing called FUD, fear, uncertainty, and doubt, it didn't make it through. It was deferred till the next meeting. So to put it mildly, I was disappointed. So I'm sitting in a room with a bunch of very smart people, and they're talking about a defect, and it happened to be defect number 684 of the working paper. What did we mean by stating the two matched result objects were the same? What does that mean? So the two objects are identical, same address, same properties at the same time, or they're distinct objects, but they have some properties in common. So it turned out to be the latter. So the meaning was clear, or was it? And then the discussion continued, and I'm sitting here and I'm going, darn these people, they didn't accept this allocator proposal, we'll have to wait till next time, and they're talking about this, and of course, you know, my tolerance was reduced. Whatever the copy constructor preserves, or as long as the two are equal, and then someone said, no, as long as they're equivalent. And then someone said, you know what I mean? And at that point, I was like, a good thing I didn't say anything. Anyway, but since it was purely a wording issue, it was left to the editor to figure out. And it's not just an editorial issue. And what it means for two objects to be the same is an important, pervasive, and recurring concept in practical software design. And it's based on the notion of value. So what do we mean by value? What does a copy constructor do? After copy construction, the resulting object is substitutable for the original one with respect to some criteria. What criteria? Think about it. Is it the same object? Are the addresses the same? Or if we do something to an object, and if we copy construct it and then do something to the copy constructed object, does the original object change? And I think the answer is no, not the same object, and certainly this isn't Java, so no to that too in general. That's not what C++ is about. So it's not that. None of this is what we mean. So now, what about same state? Would it be fair to say that the definition of value is fully delineated by saying two objects have the same value if they have the same state? How many people buy that? How many people think that's a false statement? How many people are still waiting to hear the answer? Excellent, good. Though you guys are in the right place. Okay, so let's look at this. Here's a string class, and look at this data member. Now, the bits in that variable, that data member variable, represent an address. How bad would it be if we did a bitwise copy of a string when we did a copy construction? That would be bad, right? Okay, what would happen? Two references, right, exactly. So The problem is when one gets destroyed, life is still okay, but when the second one gets destroyed, it's all bad. So we know this isn't good enough. So we need to take another step. How about the same behavior? Two objects have the same value if and only if they have the same behavior. How about that one? Anybody willing to go out on a limb and say, that's good enough, I'll take that? No. Well, all right. So I'm claiming, for now, if we apply the same sequence of operations to both objects, the observable behavior will be the same. Okay, so here's an example. I've got this function that takes a bool for now. We'll talk about why. And the first thing it does is it creates an empty vector A, and then it reserves some space on it, and then it does copy construction. So now I have a question. Tell me, is the capacity copied when you copy construct a vector? Yes, no, maybe? Okay, it depends. Can you elaborate? So in this case, it makes a copy. Is the capacity the same as the capacity on the other side, on the right-hand side, or not? Does the standard make any specification as to whether it's the same or not? Okay, at least as much I heard. Okay, the standard is silent on that one. So, depending on what your implementation is, there may or may not be an observable observable allocation when you do the copy construction. But don't worry about that. That's a special case. What about in general? Every object has a unique address. So if I pass in a bool x, and if you look at this code, when I get to the question mark colon right here, I hope this is working. Is it working? Work. What? It's hard to see. All right. Well, let me wander over here. When I get to this question mark colon, based on the address, I will either, or based on the bit, I will either get that reference to be A or B. And based on that, the output will be different. So the very fact that I have different objects, no matter how much otherwise the same they might be, their addresses alone are enough to make them not substitutable with respect to behavior. So that's just a general proof that such things happen. And if we take substitutability literally, then this isn't going to fly. So it's not true, right? Behavior is not the right answer. So now we have to work harder. And what I'm trying to say is, if this were easy, I wouldn't be giving a talk about it, and I wouldn't be revising it over the past, 15 years as I think more and more and more about it and talk to more and more and more people. So, same what? What should be the same after copy construction? That's the question that we need to answer. And it better be easy to understand, because if it's not easy to understand, it's useless. At least reasonably easy, you know? Two objects should represent the same value. Now, we haven't made a lot of progress yet, but the idea is we're trying to find a substitutability criteria that works in all cases. So, with that, what do we mean by value? We don't mean this. Okay, now we're going to talk about mathematical types. And I can't find just the right word because I don't really mean mathematical. I really mean platonic or ethereal types that are in the ether up here that we all think about, and one day we decide, gee, I'd like to approximate that in C++. So that's what I mean by mathematical type. I do not mean a literal like a semi-group or any of that stuff. I just mean some type that we want to represent in C++, but we haven't done it yet. So it's the specification in our minds. Do you see what I'm saying? Okay. A mathematical type consists of a set of globally unique values. So we've got a set, and it doesn't matter what the representation is. So heads up, this is one place where Alex Stepanoff and I have a slight, maybe different view. What just happened? That's not good. Oh, dear. Hold on. That was bad. Okay. Slightly different view in that I don't care yet what the mapping is from the ethereal type to the bit patterns in the C++ program. But that's about it. There are many ways to render the same ethereal type. In software engineering, we call that encapsulation. We're encapsulating the implementation. We really don't care what the bits are as long as they work. What we care about is the isomorphism between the approximation in C++ and the ethereal type we're trying to model. Does that make any sense? Does anybody want me to say that a different way, or you're okay? Say it a different way. Okay, thank you. So, when you go to design something, before you actually start typing, you have to think. It's a crazy thought, but you have to think about what you're trying to do. And then once having thought about it, you have this mental model in your head. I've got this thing that I want to implement, and now I'm going to figure out how I'm going to render that in C++. But before you start typing, you still have a mental model. Oh, does that make sense? Right? So the mental model is the specification, and now we're going to approximate it in C++. That's what we're talking about. And the difference I'm saying is I believe that the specific bit pattern is the reality in EOP. The bit pattern matters. I will look into that more, but that's the best I've done so far, but I'm going to have this conversation. Anyway, so a set of globally unique values independent of its particular representation. So, for example, integer. We all know what an integer is, right? And 5 is an element of the set of integers. And how we represent it, whether it's any of these different things, doesn't matter, because we're referring to the unique integer 5, that element of the set, somewhere way over there, beyond the stars. But there's one of them. There is only one integer 5. There aren't two. We cannot have two integer 5s because a set is unique, and integer is a particular mathematical or ethereal type. So there's a set of operations on this mathematical ethereal type that we would like to approximate as well. Okay. The operations will become important shortly. So for C++ type, it may be an approximation to a mathematical type, and it may not. For example, int. Int is an approximation to the mathematical type integer. There are other approximations in C++ to the mathematical type integer. For example, long int, short int, sign char, int 64, long int, right? Now, interestingly enough, unsigned is not an approximation to the mathematical type int. So, mentioning that now, and I'll probably come back to it again and try to convince you that that's the case, because the operations on an unsigned are not the same as those on an int. Unsigned approximates a different kind of algebra. As an example, I suspect many of you in here are younger than I am, and if we were to go to a class that returned age, some of you, I suspect, would have it return an unsigned. Why? Well, because your age can never be negative. So I'm going to get your age, I'm going to get my age, I'm going to subtract my age from your age, and that number will be 4 billion. That is not the algebra I choose to use. Okay, so I've said that now, we'll come back to it. The C++ object is just another representation of this global, abstract, unique value 5. Okay, so now I have this date class. And unfortunately, there's a problem with it, and I'd like somebody who should be fairly clear to tell me what's wrong with this date class before we proceed. What's wrong with it? I'm sorry, say again? The return types of the getters. What is wrong with the return types of the getters? They're wider. And why is that wrong? I want a real reason for why that's wrong. They don't represent the state. I'm good with that. That's actually important. They don't represent the state. You're right. They could be negative, but they won't be. They could be, but they won't be. Yes, good man. They're not const. Now, can anybody tell me why aren't they const? This is tough. If you've seen this before, you can't talk. Why aren't they const? No, that's why they should be const. Why aren't they const? No, they don't. These particular functions don't change the state. Anybody else? Last chance. What? They return by value. That's still not. You maybe you have an idea. What is it? In this particular case, no, because when you return by int and when you return by constant, ints aren't modifiable. Had it been user-defined type, then yes, but I don't like that either for different reasons. It's another talk. The answer is because it didn't fit on the slide. I just want to make sure you understand. All right. Now, if you notice, these are two date classes. They're trying to represent proleptic Gregorian calendar dates in the range of 111 to 12/31/9999. I'll tell you now that all the operations on these two dates are the same, and their valid range of date holding, what do I want to say, dates, is the same. Do they, if the year, month, and day correspond, represent the same value? I hear yes. That's not the main part of the talk, but that's the idea of the talk. The answer is, if they're trying to approximate the same mathematical abstraction, and if the members, if the composite value is the same member of that set, then it's reasonable to say yes. As soon as the composite value doesn't match, or if the operations are different, then that's not a reasonable thing to say. So, but the answer is yes. So these two things are the same, and we don't care about the representation, not the least little bit. Okay, so these are what we call salient attributes. Salient attributes, and I'm going to take my watch off so I can keep an eye on myself because I've been going very slowly here. Salient attributes are the set, the documented set of observable named attributes of a type T that must respectively have or refer to the same value in order for two instances of T to have referred to the same value. Okay, this is not a trick question. What are the salient attributes of a time class? This is a simply constrained attribute class. Hours, minutes, seconds, milliseconds. Do we care how it's represented? No. We care about the operations. We care about the range of values. The range of values need not be the same, but if the ranges overlap and we have a common element, that's good enough. Question. This is a reverse problem. This is a mental exercise. We never do this, but we're going to do it here because this is a conference. What would be the simplest overarching mathematical type for which std string and const char star are both approximations? List of characters. I heard list of characters. Okay, help me out. I'm trying to map that onto what I think the answer is. So one of them, let's start with this. An std string is an arbitrary string that can hold nulls, right? And const char star is not an arbitrary string, but it can be null. Right? Both can hold the empty string, but only const char star can hold null. So the answer is a nullable std string. A nullable std string would implement the simplest approximation of simplest mathematical type for which these are both approximations, neither one of which fully approximates it, right? It's an attempt. You see what the question was now with retrospect? Either one of these approximates this ethereal string, this sequence of arbitrary characters that happens to be a nullable sequence, okay? A nullable sequence of arbitrary characters. Okay, that's just a thought experiment. So now, if I represent Fred as a const char star and also as an STD string, do those two things represent the same value? If and only if they approximate the same ethereal type. Yes?
The data example you gave in talking about representing the same ethereal type, it almost sounded more like you're talking about matching interface, whereas if you're matching the same ethereal type, one could return year, month, date, and the other could return milliseconds, and they're still representing the same ethereal date.
Okay, so,
Am I missing something?
okay, now, so what was said here is the interfaces could be different. One could return milliseconds, send some epoch, and another one returns year, month, and day. And I am claiming that for the two types to be substitutable with respect to value, they better have the same interface. Okay. But I'm not going to say you're wrong, because they could represent the same time point. But that's not the same type. You see what I'm saying? In fact, the date, we'll pick one or the other. We won't pick both. We don't need two dates. We don't want two dates. All right. Anyway, this is an important concept, the idea that we're approximating the same ethereal type. Now, what about integers and integers mod 5? Are those, suppose I have 4, and one type is integers, myint, and the other one is myint mod 5. If I have 4, is it the same 4 or is it a different 4? If I have an object whose algebra is, right, I have one, there's just integers and the approximates integers. The other one approximates integers mod 5. If I take 4 and add it to itself, this is 8. And what's the other one? 3. There you go. So they're not. What? They're different. They're modeling different ethereal types. Therefore, the values that they're modeling are different, and the resulting operation, we do the same thing to both, it doesn't work out to be the same member. The operation is different, and I'm saying this is why we don't return unsigned just because the value can't be negative. It's because when it's used later in an integer context, you will get the wrong answer. This happens all the time. You don't mix integers and unsigned if you don't have to. Okay. All right. So it's an interpretation of a subset of instance state. The value is the salient attributes and not the instance state itself. It's a view on the instance state. And I use the term recursive lightly here because I want to show that there is a notion of composition. What are the salient attributes of a point? Okay, now I have a box. And what are the salient attributes of a box? There we go. Okay, and how is it recursive? Well, the origin returns a point, which is a salient attribute, and the salient attribute has salient attributes. And so it's composable. Moving on, we have a vector. Let's see if you were paying attention. What are the salient attributes of a vector? Push? Okay, I heard capacity, but how about the values of the respective elements? So if I know the size and I know the respective elements, I'm modeling a sequence of integers. That's something we can understand without having an STD vector. I believe that the ancient Greeks knew about sequences of integers well before STD vector came along. Probably Socrates and Plato talked about it. Anyway, now it was suggested capacity. How do we feel about capacity? Did Socrates know what capacity was? Plato? Anybody? Okay, so we seem to agree that is not part of value. How is the client supposed to know? They have to read the documentation, basically. Salient attributes are part of logical design. They should be natural and intuitive. They must be documented explicitly. Water break. Okay. Why is value important? Well, it turns out that when I was growing up, we didn't have IPC so much. We just worked on our own workstations, and so we just didn't care about going out of process. Once you go out of process, you have to care because you no longer necessarily have the same representation. Let's take an abstract date type. Here are a bunch of dates. These are not representations. These are the dates. These are the ethereal type. And now I create a bunch of C++ objects from a C++ date class that I wrote, and those date objects are not dates in the sense, they're not date values. They refer to date values, but they themselves are just referring to them. They are not themselves values, and this is a very important point because what could happen is, who would think of this? You might want to save those values in a database. Does that happen in the real world? We actually save data in a program to a database. We do. And so they'll be represented quite differently, and those representations will refer to the same date values. Not equal date values, mind you, the same date values. Then somebody might think, well, Java's a cool language. I'm going to extract those same values from the database. But there are no values in the database. What they're doing is they're making their Java objects refer to the same values. And it's kind of like the difference between same and photocopying. If you have an image and you photocopy it enough times in succession, the image will blur. The beautiful thing here is no matter how many times we take an object in and out of the database, it doesn't lose any of its brilliance. It's the same object. Digitally, the same object. It's the same bits. They just happen to change around because the mapping is different from databases to C++ to Java, which is why I said it's the ethereal type that matters, and the mapping is not unique. Okay, it's not just an exercise. If we don't all agree on what the integer 5 is, we can't work together as a team. Which types are naturally value types? Here's a flashlight. It's on. It's off. What's its state right now? Okay. Now. Okay. What's its value? All right. So we don't really know what its value is. And when I first wrote this, it was really twice, the pound was twice the dollar. Things have changed. All right, anyway, it's not obvious. And therefore, when we assign values to things that don't have values, we've missed something very important. If everything has a value, nothing has a value. So we have to think. What kind of objects, before I put this up, what kind of objects do not try to represent a value? Can anybody think of one? Pointers. All right, I have to say it. Pointers actually represent something in the middle. They don't represent an ethereal type because pointers are addresses in a local machine. So you can't, that's not a global property. On the other hand, they bear some resemblance. So we call them in-core value types, but they're not the same. So pointers are in between. Let's take a look at these objects. A thread pool. What would copy construction mean for a thread pool? Bad news, okay. Now, scope guard is my favorite because that is the least likely candidate, for being a value type. Its purpose in life is to manage the lifetime of some other object or resource. So scope guard, no way. Now look at these other things. Try to get a feeling for what is and isn't a value type. Okay, I heard somebody say, anything that we can't apply operations on. Is an allocator a value type? Because we can apply allocate and deallocate to an allocator, and we'll get back memory. Okay, so it was said that unless we can apply algebraic operations, I think what you mean to say is unless we can model an ethereal type that is independent of its representation in the computer, it's not a value type. Is that what I heard? But what does it mean? Yes, okay, so if you can do that, but unfortunately allocators deal with memory, and as we just said, memory is local to the machine and yada, yada, yada. Memory puts a little bit of a spin on it. We shouldn't dwell on that at all. That's another talk. So anyway, there's some truth to what you said, algebraic structure, certainly, and that's something that Alexander Stepanov makes a huge point on. And so in that sense, we're 100% in agreement. Suppose we have a Threadsafe Queue for intertask communication. Is it a value type? Its purpose for being there is to allow threads to communicate, put some work on the queue, and then take it off and work on it. Is that a value type? I'd say no. It all depends on your perspective. That's the right answer. Exactly, that's the right answer. It all depends on your perspective and the discourse and all of that good stuff. And should it support value-semantic syntax like copy construction and assignment and equality comparison and swap and those kinds of good things? Should it? It depends. What's interesting here is this is in that rare middle ground. And if the reason for the things being there has nothing to do with communicating value, but rather performing some task, then the answer is no. Okay. If we're not trying to model an ethereal type, but rather do something useful, it's a mechanism. So here's our taxonomy again, and mechanisms are on the left over here. And so let's zoom in a little bit. We've got my object type, and we're going to create this taxonomy. It's either stateless or it's stateful. By stateless, I mean it's either a bunch of functions. The way we do it is we nest them in a struct, and we make them static because we're old school. And now old school is new school because this is what we call a utility struct. And that's an important class category for us. The next one is functors, and the next one is metafunctions. And here's an example of dateutil and a static method of this struct that does something. And this is where we put non-primitive functionality that might otherwise have been placed inside the value type itself. So this is an important factoring tool. It's also a really important class category. So where is it? It's over here. All right. If we have a stateful object, it might be a mechanism or a value type. If it's a value type, it's there. If it's not, it's a mechanism. We start at the top, and if the answer is yes, it's a value type, it's over there, and no, it's over there. And if we look at the big picture again, we can come down and see that value types have a rich taxonomy. Might be a full value semantic type. It might be just an attribute class. The constraints might be complex, which means they interact. They might be simple, which means they're on a per attribute basis, or they might be unconstrained. But here's the whole picture. Okay, and these are the important class categories that we're going to talk about. By the way, an abstract interface, a pure abstract interface, is also an important category. And it doesn't come up nearly as much as the others, but when it comes up, it's something to be aware of. And we know exactly what it means. Now, having said that, what does it mean for two abstract types to compare equal? Any thoughts on that? You have a thought? Okay, they're the same type, so that's not quite enough. They refer to the same value. Well, it turns out it's a little bit of a trick question because value, if you think about it, there are no abstract interfaces in the STL, and the STL is all about value. All about value. And so the thing is that there was this fellow a long time ago who said something very important in his book, C++ Programming Style. His name is Tom Cargill. And virtual functions are for variation in behavior. And data members are for variation in value. And it just happens that it really doesn't make sense to compare apples and oranges, even though they're both fruit. because the idea is you're going to represent whatever you're going to represent, the apple, and they're going to have the same salient attributes, and that makes sense. But it doesn't really make sense to talk about things that may or may not be the same type. And as I said, it's probably an ill-conceived problem to even deal with that. Yes, it can be done, and there are all kinds of tricks and dynamic castings that you can do, but basically, that's not how we do things. So as a rule, value types are not abstract, and mechanisms, unless for performance they're not, they should be. So mechanisms are abstract, and value types are not. All right, what syntax should value types have? So value type defines the following, and I think everybody will recognize these. I don't want to belabor it. It's not about syntax, right? Ain't about the syntax. So I'm just going to put this up quickly so that we get on to the next thing. I think everybody here can read fairly quickly. These are all familiar things. These are the operations. Stepping off coals, this syntax regular. For a type to be regular, there are a few more properties it needs to have, and one of them is that it happens to be copy constructible, assignable, and comparable in linear time in the amount of bits used to represent it, and some other things too. But you got to read this wonderful little book. And in fact, the part about the whole and the parts that was talked about the other day in the keynote is the last chapter of that by Sean Parent. Is the last chapter in that little book. Little, for some definition of little. All right. These are some properties everybody knows, and they're not interesting. This one is obvious, and everybody knows it should be that way, and it's necessary. Here's one that isn't maybe quite as obvious, and most people know it, but it's always interesting. The few people in the crowd haven't thought about it before. So let me throw it out for the few of you that haven't thought about it before. If I have a D that's not part of my type, but it's some other type, and there's a conversion operation, and if it works with A equal D, it darn well better work with D equal A, or somebody's going to complain that's a bug. I think we'd all agree that's a bug if it doesn't work both ways. So, does everybody know what I'm talking about? Okay, so we'll go quickly. So I have a type T, it has an operator double equals, it's a member function, and I have this other class D, and this class D has a conversion operator. And now I try to use it one way and it works, and then I try to use it the other way and it breaks. And we all know that user-defined conversion on the left-hand side of a member operator doesn't happen. So it's not symmetric. So what's the solution? Don't do that. Do this. Then it works, and everybody's happy. There's always a wise person that comes along when we have a little bit more interesting class. So we have a string, and we're going to make operator double equals on string, and string's a free function. We're going to make the one with the care star on the left-hand side free as well, so that conversion can work. But why bother with the one on the right-hand side? That's just a waste of time. I'm not going to do that. So, of course, we have the even smarter person come along with class foo and class bar, and then we do bar equal foo, and that works. And then when we swap them, the conversion to string on the left-hand side fails. And, oh well. So don't be cute. Don't do it. Just make all your operators, double equal operators free, and life will be great. Free operators. And by the way, all of these should be free, but not these. Okay? And then we can talk about pre-increment and post-increment in another talk. All right, we'll talk about it now. Pre-increment is a member. Post-increment is free. Go figure. Okay. What semantics should value type operations have? So, the important thing is that whatever you're going to do is derived from the state of the object itself and nothing else. It has to be only the bits that are in the objects. And we're saying that these salient attributes must respectively refer to the same value, corresponding fields or attributes refer to the same value. Okay. Now, when we say the same value, again, in that wonderful meeting back in 2007, they started talking about what the copy constructor does. But if you look at this, the copy constructor may or may not copy capacity, and therefore, the copy constructor implementation is not sufficient, if we're archaeologists, to figure out what the true value of the object is. Can't tell us. So copy construction is not the right place to start. However, comparing something equal, we do that with operator equal equal. And the nice thing about operator equal equal is the implementation of operator equal equal is the operational definition of value. That's the implementation. And the documentation, the function level specification of operator double equals is the definition of value in the interface. That is the contract. That's what it means. Okay? They share many properties that are objectively verifiable. They should be intuitive. Here's something, this is a slide taken from my 2008 presentation. It was so good I had to put it back into this. It's been hiding. So tell me if people know about CMOS and NMOS technology, ancient technology, NMOS. And these are two registers, and they each hold 8 bits. And I assume that a sequence of bits is a value, right? A sequence of bits, we all agree, a sequence of 8 bits is a value. And I'm going to say that the technology is orthogonal to that value. What do I mean by that? I don't care what the technology is. Could be an alligator. I don't care. Could be a lock. It's not relevant to value. Now, we see these are not equal. But I'm going to do an assignment. Now, if I do an assignment, what's going to happen? Anybody, what's going to happen? It's going to copy the value. What exactly is the value? Okay, you know the bits don't actually flow through the wire, right? It's the voltage on the nodes that changes, right? The information travels. So you're saying this happens. No. The information happens, but not the transistors don't flow through the wires into the other register and turn it into a CMOS transistor. Okay. So this is not what we want to mean by assignment. And the big concern is, suppose we just assign the V-table pointer while we're at it, or maybe the alligator. These are equally silly concepts because the V-table pointer and the alligator are part of the runtime type of the object. Even if they're using the polymorphic memory mechanism, we do not want to propagate alligators in this way. Just throwing that out there. Don't do this. Okay. Knowing what salient attributes are will help us with testing, but that's, again, another topic. So suppose we have A, B, and C objects of type T. D is an object of some other type. Assuming it exists. Now, why wouldn't it exist? Is it possible that we could have a value-semantic type and have it not have an operator double equals, or is that just impossible? Is a singleton a value-semantic type? I'd be interested. Think about it. So the question is, would we ever have a value-semantic type that didn't have an operator double equals? Is it even thinkable? Function? Why wouldn't it have an operator double equals? That might be a good answer. We don't know how to do it? That would be a good answer. Do we know what it means for two functions to have the same value? Yes? Okay, so you're saying the definition of value for a function is that they do the same thing on all inputs. Okay? But if they have different function pointers coming in, that's a hard problem. Do you know how hard it is? I think that's a good answer. I believe it's undecidable. I think it's the same as the halting problem. Anyway, we'll talk more about hard problems later. Sometimes almost regular is good enough, and it happens that there's a very special kind of regular type that is almost regular, and Alex Stepanov calls it semi-regular. It's regular in its syntax and all of its semantic properties, but the operator double equals and operator not equals is missing. So think about why it might be missing. We'll talk more about that a little later. Okay. And again, the value of A is independent of any external object state. Any change to A must be accomplished via A's interface. I'm just checking our time. Suppose a value-semantic object refers to another autonomous object in memory. This is the example where we have the in-core semantics. This is not part of the talk, but we can have a pointer and an index, and here you see the pointer, and here you see the index, and we have bool operator double equals, and two element objects have the same value if they, one, refer to the same record object in the current process, and two, have the same element index. So here's our wonderful example where we have a bunch of element pointers, and we have two prospective record objects. And if you look at this, two of these objects have the same in-core value. Does this matter? Does it matter whether record object A and record object B have the same value? They're autonomous objects. The answer is no, they might not even be value semantic. We don't care. What we care about is that object 2 and object 3 refer to the same object, the same autonomous object, and they have the same salient attribute, which is the index into the object, and so these guys compare equal. Why is this important? Because it's an autonomous object, it could change. Even if it did have value semantics, and there were two of them, one could change. But if that one changes, it doesn't matter because it changes for both of them in lockstep. But this is not part of the talk. This is just to keep a placeholder so that you know there's a lot more to talk about later. It's not full value semantics, so again, not the focus of today's talk. Okay. What do we mean by properly? So this is sort of a big point. We got off to a little bit of a late start, and I'm going slowly. I just want to say that if people want to go out and get food at exactly 3:15, or is it 4:15, I can just stop right there. So we'll do that because last time I didn't get any food, but that's okay. So I'm just going to stop exactly. When you say it's time, that's it. How many, 5 minutes? Okay. So we agreed that the same observable behavior wasn't enough. We might allocate memory. But this is the big takeaway for this hour. If A and B initially have the same value, and the same operation is applied to each object, then, absent any exceptions, undefined behavior, craziness, order of operations, machine size, whatever, they will again have the same value, or they never did. This is huge. This is subtle essential property of value. If you write a value type and this does not hold, your value type is broken in a profound way that's not intuitive. It's not substitutable. All right. Deciding what's not salient is hugely important, and there's a lot more to this story. I want to point out that this is not a test driver. Kevlin Henning made me point this out. This is a sequence of operations. We're saying if we do this to the same C++ type, then it will again have the same value. Now, here's a thought experiment. Suppose we had a homegrown ordered set, and we were able to set a bit at construction that changed the order from being less to more. So I create two objects, they're empty. One is set to increasing, the other is set to decreasing. The question is, they're both empty, do they represent the same value? No, I heard no. Does anybody think yes? Okay, Mr. Yes, we're going to add 5 to both of them. Append 5. Now each of them has 5 in it. Do they have the same value? Now I'm going to put 6 in. One of them represents the ordered set 5, 6, and the other one's 6, 5. Remember, the name is ordered set. Do they represent the same value? Okay, I hear a yes again. That's interesting because it's an ordered set. Not sure why. But no, it's an ordered set. The word specifically, ordered set. Ordered set means sequence. It's unique. Ordered set means it's a sequence of unique elements. That's what it means. Excellent. No to all of those. I know, look, we use terms that, look, what can I do? I'm trying to use the standard library. We have unordered set and we have set. Implicitly, set is ordered. What do you want? Okay. I understand the problem, believe me. All right, so I've gotten through all of this. So they're not equal. That was the main point. And this is also, now remember, these operations have to be salient. Originally, unordered set was called hash set. And hash set has all kinds of ways to violate the intent of the ethereal type that most people think it's trying to approximate. So you can discount all of those operations as irrelevant. And think about what the ethereal type would do and do that. Okay. Okay, what makes 2 unordered containers represent the same value? And I think I'm going to end with this, maybe. If I have a bag of Halloween candy, 2 kids, they each have a bag of Halloween candy. How would you ask the question, do those bags have the same value? Yes.
Every element within the bag has the same value?
Is it a homogeneous collection? No, Halloween candy is not homogeneous. What you do is you take the 2 things of candy, you lay them out on the ground, and you permute one to see if it can match the other corresponding elements. If they have the same number of elements and corresponding elements have the same value as determined by the elements, then those 2 multi-sets have the same value, otherwise they don't. And where's Pablo? Is he here? Oh, he's not here. Oh, yeah, that's right, he was tired. Anyway, in 2010, we actually got that definition into the standard in time for 2011. It was a good thing. Yeah?
Wasn't there earlier you made a comment about it being able to do it in linear time?
That's a Stepanov requirement. Okay, that's what we mean by what Stepanov calls a regular type. Now, keep in mind that everything having to do with hash maps violates that, everything, right? There was a suggestion that we could solve that problem by having order be salient in an unordered set. We decided not to do that because that's just silly. Okay. I think this is probably a good place to stop right here. Remember that it has to be the same type. As soon as you change types and they're different approximations, then all bets are off. This is undefined behavior. Okay.